Hello and welcome to another LeetCode problem. Today we're going to be doing the problem of the day for June 9th, and it's find smallest letter greater than target. And so this one's pretty straightforward. It says you're given an array of letters sorted in non-decreasing order in a character target. There are at least two different characters and letters. Return the smallest character and letter that is lexicographically greater than target. If such a character does not exist, return the first character and letters. So what we can do, imagine instead of having this like target and characters, imagine if we just have numbers, right? So let's just say we have, let's just say we have like a target of 1 in this example, and then our letters would be like 2, 3, 4. So how would we do this? And this would be the same way that we would do this. We would simply, what would be like the easiest thing to do? Well, the easiest thing to do is just go right to left, right? And keep checking if the character is bigger than the target, and if it's not, stop, right? So we can check this. It's bigger, yes. It's bigger, yes. It's bigger, yes. And then the last character that's greater than target is our answer. So like, let's say we had a 0 here, then we would say yes, 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 no. And that means this would be the character. However, the problem with this method is it's going to be linear time, right? We have to search through the entire array. And so what we could do is, like I said in a lot of my other videos, when you have a sorted array and you're trying to look for a target, the best thing to do generally pretty much is a binary search. And so we're going to do kind of the same thing, except now instead of doing that, instead of searching linearly, we're going to be doing a binary search. So we're just going to take some middle index and we're going to ask ourselves like, okay, is this greater than or less than target? Okay, well, it's greater. Fine. Let's record this index we saw. And if this is greater, then we have to check to the left to see if there's anything else that's greater. And if it's less than target, right, like let's say we have something like this. 1, 2, 3, 4, 5. And let's say our target is 3. Or 2. Let's say our target's 5, actually. We can even do this, like 6. Okay, so we'd get to some middle element and we'd say, okay, this is smaller than target, which means we don't store this index as something we've encountered. And we're obviously going to search over here. And so if the number is smaller than target, we're going to search to the right. If the number is greater than target, we're going to search to the left. And we're also going to record that number. And then we're just going to search to the left, but we're going to record the number. And then whatever number we last recorded is the number that's, greater, like the first one greater than or equal to a target. So let's kind of walk through how this will work for this example. So let's say we have these indices 0, 1, 2, 3, 4, 5, 6, and we have a res here. And then we can just make so we're going to make a number to start off. So we'll just say, because we want a number greater than target, we'll just make res infinity. We want the smallest number greater than target. We're trying to minimize it, right? So we'll just make it infinity. And I think there's guaranteed to be an output, but even if there isn't, we can just check at the end, is our res infinity? If yes, then there is no number greater. But anyway, so let's see how this would work. So we would do a binary search. So the binary search takes the middle of the array. And if there's 2 elements in the middle, it's going to take the leftmost one. So we're going to go over here and we're going to ask ourselves, and there's going to be a left and a right, bound for the binary search. So when we take this middle, we're going to ask ourselves, is this smaller or greater than target? It's smaller. So we need to search to the right. So if we need to search to the right, we need to update our left pointer to be over here. Okay, now we get a middle again. So we're over here. Is this smaller or greater than target? Well, it actually equals target. And so if it equals target, we want numbers that are greater than target. So we need to search to the right again, right? So then once again, we update our left to be over here. And now our left and the right are the same value. And so we would get the 6, and that would be our result. That's kind of how it would work. It's just a standard binary search algorithm, pretty straightforward. We just record numbers that we see along the way, and then the last one we find. I like to do it this way, where I don't like to break. Like you could do something like, you could say if you're like, let's say you get to a number, right? Let's say you're looking for number 3. And you have 1, 2, 3, 4, 5, 6. And you say you're looking for a number greater than 3. And you get to this 4 and you say, you can technically have a thing saying like, oh, if my number is right after the one I'm looking for, then that has to be the result. So you could technically do this, but then you have to do more comparisons and the time complexity is not going to change. Like when you do a full binary search of something, it's still going to be log n. It's not going to be any slower, but then you have to do more comparisons and there's more edge cases. So I prefer just doing a binary search until I'm out of bounds, and then just storing whatever number is the smallest. So let's code that up. So we're going to have a res equals infinity. Yeah. Now I compared these with letters, but so actually instead of res being infinity, we just need something that's greater than the greatest than z, and I think that's something like zz would be greater than z technically. We could also get the ASCII value, but this would work as well. So this would be kind of like our infinity, quote unquote. Okay, and so now we would do the rest of it would be the same. We can just compare characters with a greater than or equal to type thing. So now we have a left and a right, just like in normal binary search. Length letters. Okay, that's -1. So standard binary search algorithm. Okay, so we need a pivot value. And so remember our cases, if letters pivot, so one case is it's equal to target. Then remember we need to go to the right because we need the greater element. So that's going to be left equals pivot +1. If letters pivot is less than target. So actually what we could do here is we can combine these. So if it's less than or equal to target here, we can combine that. Because we're going to go the same way. If it's less than or equal to, we need to go right. So we could do that. Okay, now we can have an else here. So else, what we need to do is we need to update our res, right? So res equals, so I don't think you could do a min, but I can just have an if here. So if res is greater than, yeah, letters pivot, then we need to update our res. So we also want, yeah, so we want the letter, we don't want the index, so we can just update directly. So then it's gonna be, okay, so we updated it. Now this is the case, remember that we are greater than target, so now we need to go left. So we need to do right equals pivot -1. Now we're just gonna do this whole binary search till it's done, and then we can just return res. And then we'll just say we'll return res if res does not equal zz. This actually, I think upper might be before, so let's just do this just in case. Okay, else res. So we're just saying if we found something that's smaller than zz, which would be any letter, then we can return. Otherwise, we want to return if the letter does not exist. Yeah, return the first character in letters. Here we go. So we want the first character in letters. So less letters. Yeah, 0. Okay, that should work, I think. Yeah. Okay, cool. So it's pretty straightforward. What you could do if you don't want to do this letter comparison is there's something in Python or another language is called ORD, I think, which gives you the ASCII value of a letter. And so then you can make res equals like infinity, and then you could do ORD of all these letters, which would give you the ASCII value, and compare ASCII values. That works as well. But anyway, let's think of the time and space complexity. So for a binary search, the time is n log n, because the most times, like the longest it can be is actually, sorry, it's not n log n, it's log n. Yeah. So for our binary search, it's log n. It should be slower, faster than linear time, because we're dividing our output by 2 every time. So if we have something length like 1,000, we're cutting off half every time, right? So we're dividing by 2, getting 500, dividing by 2, getting 250, and so on. And so when you keep dividing by 2, then it would be something like 2 to the n equals whatever our length is, and then n equals log base 2 of the length, which is n. Okay, and so that's the time. And for the space, we didn't make anything else. We just used this left and right and res, so that's constant space. So that's going to be a big one. Okay, so hopefully you liked this problem. It was definitely kind of easy. And if you did, please like and subscribe to the video. And I'll see you in the next one. Thanks for watching.